if you remember, we had, for example, W such that W is a palindrome. Right? This was our language. So languages are sets. Sets are problems. Strings in the language means the answer is yes. Strings not in the language means the answer is no/false. So we initially started looking at decision problems as what is the simplest machine I can use to solve the problem? A DFA, an NFA, a PDA, Turing machines. Then in midterm 2, we analyzed complexity not by the simplest device needed to solve the problem, but by the runtime of the problem. N squared, N cubed, et cetera, et cetera. Now, we're going to apply a new level of categorization to the same set of decision problems. So one thing to remember here is all of these refer to decision problems only, if the answer is yes or no. It's not, you're never going to be asked about, for example, an integer output. You are given inputs, and you wish to decide if the answer is true or false. So, thought experiment, can any question be converted into a decision question? Where the answer is true or false. Can maximization questions be converted into decision questions, like on the last quiz? When we asked you to find like the biggest value of k, what we did is we essentially tried all possible values of k. So if I say find the maximum value in the set, another way of rephrasing that as a decision question is given a set and an integer k, is k the maximum in this set, yes or no? So any problem, trivially, can be converted into a decision problem. So we'll start there as fundamentals. A problem is said to be in P if a deterministic Turing machine can solve the problem in polynomial time and output yes or no. A problem is said to be an NP if you can verify the answer in polynomial time. By that, I mean, I give you the problem, I give you my answer, and I give you proof that the answer is correct. So, for example, let's say, does this graph have a Hamiltonian path? I give you a graph G, so we have O of V plus E inputs. I give you an answer true. I claim it has a path. And then I give you the path itself. Can you check if I'm lying or not? Well, yes, you just trace through the path and see if every vertex is hit. Another example of this, you have a Boolean formula phi, and the question is phi satisfiable? Is this problem in NP? Yes, because if I give you a Boolean formula as input, if I give you the actual satisfying assignment as proof, you can simply iterate through all of the clauses and make sure that they're all true. So a problem is in NP if yes instances, whenever the answer is true, with sufficient proof, you can verify in polynomial time. The more formal definition, so the proof is what we call a certificate, and the algorithm to verify that the certificate indeed proves your answer is called a certifier. So formally, if I wanted to prove that, let's go to the quiz question. Is k the length of the longest increasing subsequence, or is there, what was the quiz question? What was it?
Given a list, L, and given integer k, is there a longest increasing subsequence
of size k? Okay, is there, yeah, okay. So given a list and given an, yeah.
That wasn't it. It was like, given the longest subsequence of A, is this greater than K?
Okay, we'll pick a problem. Given a list, given an integer k, is k the length of the longest increasing subsequence? Let's fix that as a problem. How would I prove, can this be proved in polynomial time? Okay, let's make it even simpler. Given a list and given an integer k, is there a increasing subsequence of size k? So I'm not asking for the maximum. Given a list and given an integer k, is there an increasing subsequence of size k? How would I prove it? Well, if the answer is yes, I take in the list. The certifier algorithm also takes in proof, which is the subsequence itself of size k, and you simply iterate in polynomial time and make sure that that list is increasing. So that's what a problem means to be NP. Questions about that? A problem is NP hard if you can reduce from a known NP hard problem to it. So the definition is a bit circular, but if you're curious as to why, I'll go like in office hours or another time. But this definition is if X is a known NP hard problem, Y is, let's say, the mystery problem that you're trying to prove is NP hard. So trying to prove that's NP hard. If you can reduce from X to Y, that is, assume you have a magical black box for Y. If you can find a polynomial time reduction, this is polynomial time, from X to Y, then the problem is NP hard. Finally, a problem is NP complete if it's both in NP and NP hard. So once again, a problem is in P if, given a problem, you can output yes or no in polynomial time. A problem is in NP if I give you the problem and the answer is yes, and I give you proof that the answer is yes, you can verify the answer in polynomial time. A problem is NP hard if you can reduce from a known NP hard problem to it. And a problem is NP complete if it is both in NP and NP hard. Those are fundamental definitions that are important. So we'll get started here. Given an undirected, so it's saying prove each of the following problems is NP hard. Given an undirected graph G, does G contain a simple path that visits all but 374 vertices? So you want to know the decision problem, true or false. You're given a graph. Is there a path that visits all but 374 vertices? You want to prove that this problem is NP hard. So let's start here. Before we prove it's NP hard, is this problem in NP? Yeah. Oh, exponential time is just the set of all problems you can solve within exponential time. So that every P is a subset of exponential time, at most in exponential time. So it's sort of like big O of n cubed includes problems that are solvable in constant time. This means like you can solve it within exponential time. So you can solve any polynomial problem in less than exponential time. Anyways, so is this problem in NP? Yes or no? Okay, why? Okay, so what is the certificate and what does the certifier algorithm do? So let's write it formally, certifier. It's going to take in a problem instance. We'll call the problem instance in this case G, because it's the graph. This is my problem instance. Okay. What should the certificate be? The path itself. Okay, good. And then what should the certifier return? How should it return true or false? Yeah, exactly. So how do I do that? DFS, right? Run DFS on the first vertex in the path. Count the number of nodes visited. Let's call this n. If n is equal to the number of vertices in the graph minus 374, return true. Else return false. So this is proving that it's an NP, but that's not what we're asked to prove. We're asked to prove that it's NP hard. So to prove that a problem is NP hard, we reduce from a known NP hard problem So we'll call this P1. Try to prove, which is the problem we're trying to prove is NP-hard. And this is a known NP-hard problem. So we're trying to go from a known NP-hard problem. We have a black box on the desk that tells us, if I give it a graph G, it answers this question for us. Is there a path that visits all but 374 vertices? What problem is this similar to, and why? So we need to find a target for the reduction. We need to find a known NP-hard problem that's similar to asking if you visit all but 374 vertices. So if you can't think of one, let's start with the constants. Is there any reason they chose 374? Probably not. What if I asked you, is there a path that visits all but one vertex? Would that problem be NP-hard? What if I made it all but 0 vertices? That means it visits every vertex. What is that problem? Hamiltonian path, right? So the constant here has real no meaning. I changed it to 1, and then I'm like, okay, all but 0 vertices. So they could have chosen 1,000, and I don't think it would have made a difference here. So this problem is similar, so it sounds similar to Hamiltonian path. And then this is just for your sake, just to make sure we're clear on the definitions. The Hamiltonian path problem takes as input. You wouldn't need to write all this on an exam, but I want to be clear what you need. You're taking as an input a graph G, and then you output true if there is a path that visits every vertex exactly once, false otherwise. Okay, so this problem seems similar to Hamiltonian path, so I'm going to fix the known NP-hard problem to be Hamiltonian path. This is now Hamiltonian path. I know that my input into the Hamiltonian path is a graph G. So I know that. And then the problem that I'm trying to prove takes in a graph G prime. So what should my reduction look like is the next question. This reduction is what we are trying to build now. So I have a black box on the desk that tells me, if I give it a graph, does this graph contain a path that visits all but 374 vertices? Using it as a black box, I am trying to solve the problem of, if somebody gives me a graph, is there a path that visits every single vertex? How can I use the black box that tells me if there's a path that visits all but 374 vertices as an oracle to solve my problem of, given a graph, is there a path that visits every vertex? Yeah? Could you try running 374 at random? Meaning?
Reading it 374 random and then running it.
Yeah, so you're saying, okay, this tells us, hey, does it visit all but 374? So how many possible ways can I get rid of 374 vertices? N choose 374. Let's say I did that. So that would take a lot of time, first of all. And then, second of all, if you remove a vertex, should you remove all of the incoming and outgoing edges to this? Yeah, okay. Take your idea and reverse it. Instead of removing 374 vertices, what could you do? What's the opposite of removing? So now add 374 vertices. It's a bit backwards, but think about it. So my original graph had a Hamiltonian path, G. I added 374 nodes that are completely disconnected from the original graph. I pass it into a black box on the desk that takes in a graph and tells me, do I have a Hamiltonian path that visits all but 374 vertices? It says, yeah, this has a Hamiltonian path, and these 374 vertices that I added are completely ignored. Does that make sense? So essentially, if my graph G looked something like this, so if G was a graph that looked something like this, then G prime, our reduction, has to map a graph that looks like this into this, where this is my original G, and then you add in 374 disconnected nodes. So again, I'm trying to solve the problem, does this have a Hamiltonian path? I have a black box on the desk that tells me, given a graph, do I have a path that visits all but 374 vertices? Yes, I do. So if G has a Hamiltonian path, G prime will have a Hamiltonian path that visits all but 374. So you need to prove this in two directions. So first we should describe the reduction. So here's what you would want to write on an exam. You would want to describe the reduction first. So construct G prime as follows. You can take the graph G, which has the vertex set v comma e, and you can say v union d1 d374, where d are disconnected dummy nodes, and their labels with labels, they need to not already be in the vertex set, so with labels distinct from V. I do not need to add any edges, so we can say V prime looks like this. E prime can just be the original edge set, and then you construct G prime by using V prime, and Jesus Christ, this sucks. Yeah.
Why would they all be disconnected? Wouldn't they have to be connected?
All but 374 vertices.
Like, wouldn't you have to connect all of them so it visits each one once? Like, isn't that a definition?
No,
Am I misunderstanding?
so you're saying, do these vertices need to be connected? You're asking about the 374 that I've added?
Yeah, because it's in Hamiltonian.
So the original graph, it visits, so this path, so G prime is a black box on the desk that tells me, given a graph, is there a path that visits all but 374? So it visits all these three, but then it does not visit these 374. So you could connect them if you wanted, but as long as these are not connected to this, you're okay. Yeah, it's a little bit tricky. And I lost my pencil. Where? Thanks. Okay, this thing also sucks. Great. So this is how we make our construction. So you would first describe the reduction. The second thing that you would do is prove in the forward direction. So what this proof says is if G has a Hamiltonian path, G prime has a Hamiltonian path that visits all but 374 vertices. So how do you do that? So if G has a Hamiltonian path, the reduction, you can justify it simply. You don't need to write an essay here. Reduction adds 374 disconnected vertices. Did vertices. Which means G prime has the same path as G, Hamiltonian path that the original vertices of G had. Original vertices of G had with 374 on visited ones. And then in the reverse direction, I'm not going to write it out, but you need to prove both ways. Now I need to say if G prime has a Hamiltonian path that visits all but 374 vertices, then since my reduction did not add any edges in, all of the edges must have been a part of the original graph G. Since they were part of the original graph G, they form a Hamiltonian path. So we'll write that quickly. In the reverse direction, if G prime has a Hamiltonian path that visits all but 374 vertices, then we know that any edge in G prime must have come from the original graph G which means G has a Hamiltonian path. So you need to justify that this reduction is true in both ways. So we have the reduction, we have the proof. So this would be sufficient to prove that the problem is NP hard. So the first thing that I did is I proved that it was an NP. This was not asked in the question, but I'm doing it because it's good practice. Then I proved it was NP hard. And then let's say I put this question on your quiz and then asked you to circle all of the complexity classes it belongs to. Let's ask, is this problem NP complete? If I said to select it, would you select it or not? Yes, because it is both in NP and NP hard. And then, is this problem solvable in exponential time? Yes, because I can just take all n choose 374 vertices, brute force run DFS, make sure that at least one of them is connected. So this is also yes. Does anyone have questions about how to prove a problem is NP hard? Yeah.
Why do you have to prove the opposite direction?
So why do I need to prove the opposite direction? Let's take a look at his point. So in order for a reduction to hold true, I'm trying to reduce A to B. If the answer to A is yes, then I want the answer for B to be yes. If the answer to A is no, I want the answer for B to be no. So that's saying, so this is important. Let's say if the answer to A is yes, then I want the answer for B to also be yes. If the answer to A is no, then I want the answer for B to be no. There is,
You're just checking.
so in logic courses, when you say P implies Q, this is equivalent to saying not Q implies not P, which is just checking the reverse direction. So this is what we're doing to check the other direction. Yeah. Okay. In this problem, I just articulated it. I didn't write it down. So in every proof, pick a target problem, pick a known problem, pick the known problem that you have and pick a target problem. The reduction needs to be polynomial in time. Make sure yes instances map to yes instances and no instances map to no instances. Another way of saying that, exactly what he said, is make sure that if the answer to yes, yes, no, no is the same thing as saying yes, yes, and then if the answer to this is yes, the answer to this is yes. Yeah.
How do you know what to choose if you have no problem? Not
Yeah, it's hard.
what does it sound like, but in the sense of what do you know is what do we agree is a known hard problem?
Yeah, so there's Cook-Levin published, I think, a paper with 300. I'm not saying go read this paper, but what happened is this dude basically wrote a paper saying 3-sat is NP hard, and by the way, from 3-sat, I can form reductions to all of these other problems, and therefore all of these other problems are also NP hard. So we'll use those as known NP hard problems. Yeah, so there's reductions from 3-sat to Hamiltonian path. On the cheat sheet for the exam, there's a list of known problems. And then if you go to the course website, under either this lecture or the previous one, I proved that solving a jigsaw puzzle is NP hard. Yeah. Okay, take a look at this problem. Classification. In the following problem in P, is the following problem in P, NP, or some combination of the complexity classes? For each of the following problems, circle the complexity classes that it belongs to. So your input is a graph G, and your output is true if there's a path. If there exists a path that is at least 374 vertices long. So is the problem P, NP, NP hard, NP complete? What do you guys think? Right, it's definitely NP because if I give you the graph and I give you a path, you can check that the path is 374 nodes long, and you can check that the path actually exists in the graph just by running DFS. So it's definitely an NP. So I would circle this one. Is it NP hard or not? What do you think? Or if you're not thinking, that's okay too. So the problem that we just solved asked all but 374. This problem is asking 374 exactly. Yeah, so let's play the same game with constants. True if there is a path that is at least one vertex long. How hard is that to solve? Can you find a path that is one vertex long? Okay, what if I ask you about a path of length 2? Yes, you can do that easily in polynomial time. If I ask you for a path of length 3, you can do that easily in polynomial time. So this problem is actually in P. 5, 4, 6, 7. This problem is in P. Oh, wow, it changed. Okay, yeah, this problem belongs to P because the algorithm is literally run DFS from a single node, and DFS will give you a traversal of the entire graph. You can find the depth of any node, and then if the depth of that node is, if there is a node with depth 374 or bigger, you know that it's possible. There are many ways. You can say, I'm going to do pre-post order numbering and then check if there's a post order numbering of at least 374, right? Many ways to solve this problem in polynomial time. So the point is, it's very easy to construct questions that look similar to NP hard problems, but if you stop and think about them, are actually solvable in polynomial time. Let me give you one more example. So I say that you have let's call this problem almost sat. So he loves taking variants of sat. You have an input formula phi. Okay, so phi is your input. And then it's 3 CNF. So recall that looks like A or B or C and D or E. Raymond, this one is and, right? Yeah. Okay, cool. It's a 3 CNF formula. And then your output is true or false. If phi has at least 2 satisfying clauses, or at least if phi can have, or if, sorry, there's a satisfying assignment okay? So you're given a 3 CNF formula, and I want you to output true or false if there's a satisfying assignment where at least 2 clauses of phi is satisfiable. And then I'll also tell you that phi has at least 100 clauses. Okay? That should help you. So originally we think, okay, 3-sat. 3-sat is known to be NP hard. But I'm not asking you if the entire formula is satisfiable. I'm asking you if you can satisfy exactly 2 clauses. Is this problem in P, NP, NP hard, NP complete, X time? Okay, is it solvable? Let's start here. The easiest one to check is NP. If I give you phi, and I give you 2 clauses, and I give you an assignment for those 2 clauses, can you check in polynomial time if those 2 clauses are satisfied? Okay, great. So we know it's an NP. Now the decision is it NP hard or is it in P? By the way, please, if you select NP and NP hard, always circle NP complete. Like, don't forget to do that. But anyways, so now is this problem solvable in polynomial time? It's a 3CNF formula which has this structure. Does there exist 2 clauses that are satisfiable? Can I solve this in polynomial time, or do I need to reduce from 3-sat to it? Let's make this clear. You cannot repeat literals and clauses. Within a clause. Okay? Here is a clause of let's make it as restrictive as possible, let's say. Can somebody give me a 3CNF formula with 2 clauses where you don't repeat literals, where it's not satisfiable? Is this formula satisfiable? Can you come up with a value of true or false for A, B, and C that will make this be true? Okay, give me one trivially. Set A to be true, and then set B to be false, and then this is satisfiable. Okay. Is there any way for this to be unsatisfiable? Can someone give me an assignment of true and false values to A, B, or C where this formula evaluates to false? Yeah. Right, so this is all true. True, true, true. This becomes that, and then this whole thing becomes false. Okay. But is this satisfiable as 2 clauses? Yes, we can find a satisfying assignment. So let's put it this way. Let's try to construct the worst case scenario. I cannot repeat literals within a single clause, but I can repeat literals across clauses. Any new variable that I introduce will only give me more freedom to make phi satisfiable. So let's try to construct the most restrictive set of clauses possible. So now I want you to think about this problem again. You're given a 3CNF formula. Phi has at least 100 clauses, and I'm asking you, is there a satisfying assignment where at least 2 clauses are satisfied? Yes or no? And is the problem in P, NP, NP hard, NP complete? So we got NP. Now, either reduce from a known NP hard problem or argue that it's in P. Okay, let's say I just gave you literally 2 clauses, and then I asked you, is there a satisfying assignment? So you have 2 clauses. How many possible ways are there to assign true and false values to 2 clauses at most? So I have 2 to the 2 times 2 times 2, which is 8 here, and I have 2 times 2 times, let's say this was DEF. I have 8 here. So I have 16 possible assignments for 2 arbitrary clauses, right? For every pair of 2 clauses, that's n squared time, try the 16 assignments. if it's true, return true. If at least one of them returns true, return true. Otherwise, return false. Yeah.
You mean eight different assignments?
In this case, yes. But I'm saying if you had DEF. But there is a one-line answer to this question that would prove that it's in P. So you would circle P, and then you can answer this in, yeah, a single line. Hint, can you give me two clauses where, two 3CNF clauses where there's no satisfying assignment? Can you generate two clauses? So I'm asking for phi. Phi has two clauses, and there is no satisfying assignment to them. Is that possible? So something like this, where you have something or something or something, and something or something or something, can you think of a formula in that form where there is no satisfying assignment at all? This guy's shaking his head no. Why?
I mean, you just said this one is satisfiable based on the inputs.
Right. I'm saying of this form as in like any three variables or together and any three variables or together. Can you come up with an unsatisfiable formula with,
I think you can.
right,
unless the literals are
repeated, but
for this.
right, but you can't repeat the literals.
Yeah.
So the answer to this, to prove that it's in P, is return true. That's it. Because we're not asking you to find the assignment, we're asking, is there a satisfying assignment? So the original phi problem, the 3-sat problem, asks, is there a satisfying assignment? And you're asked, is there a satisfying assignment for exactly or at least two clauses? Well, there always will be in this case. What is the minimum number of clauses you need to make an unsatisfiable formula with three variables? Okay, with two variables, how many do you need? With one variable, let's say the clause had one variable. How many, what's the minimum number of clauses you need to make an unsatisfiable formula? Okay, A and A complement. With two variables, how many would you need?
4.
Then for 3, how many would you need?
8.
So if I ask you, are at least 2 satisfiable, and it's a 3CNF formula, the answer is always yes. So you need to think about looking at a problem. Before you try to reduce, you look at this problem and you're like, can I write a polynomial time algorithm to solve this problem? Is there an efficient way for me to solve it? If you struggle to come up with that, then start suspecting that the problem is NP hard. If you suspect it's NP hard, try changing constants, varying parameters, and seeing if you can make it similar to a known NP hard problem. Okay, enjoy your weekend, everybody. I have office hours in the room down there if anyone has questions.